Okay, so how's everybody feeling today? Feeling good about wrapping up the semester? Almost done. The light at the end of the tunnel. So we're done learning new stuff now, or at least I'm done teaching you new stuff. So I'm going to review some things, which in some cases may mean that you're just learning it, but it was intended that you had learned it before. So basically, this class and the next one will be us sort of recapping what the course was about, and then trying to prep you for the exam so that you don't blow that. It's worth a lot, so it's 2 hours of your life that basically can destroy or it can't fix a semester's worth of neglect, but it can destroy a semester's worth of hard work. So I don't want you guys to blow it. So we'll start with a review, and then I'll go down and break down the structure of the exam and the sort of breakdown of topics, so you know what kinds of things to focus on. So let's just start. And although maybe this isn't the ideal way to do it, I'll stick with my usual lecture format of just entering stuff, of typing stuff up in front of you. So when we teach a course, yep?
Will a job be on the exam?
Yes.
Roughly how will that be split? Will you like half?
We'll get to that. Yeah. So we'll get to the breakdown of topics on the exam and number of points per topic. But when you decide you want to teach somebody something, or you decide you want to teach a course, the first thing that one should look at are what the point of the course is. And in learning terminology, these things are called learning objectives. So at the end of the course, when the course is done, what should students in this course know how to do? And so for us, for this course, it's your first, it's introduction to programming, introduction to computer science, introduction to a lot of different things. But the first thing on our list of learning objectives is that you become proficient in some programming language. So that you become a decent programmer in some language. And in this case, we chose Python because while it's easier to become proficient in Python than in some of the more sophisticated languages. So that was the first goal of this course. Now, this isn't just about learning Python syntax and what all of the things mean, all of the different constructs in Python mean. Sort of related goal and something that you need to do any kind of programming is learning how to solve computational problems. So these are problems where someone gives you a well-defined input and asks you for a well-defined answer. So someone says, here's a list of numbers, give me the biggest number. Or here's a list of numbers, return the sum of this list of numbers. Or here's a list of files that contain MP4s or MP3 songs or MP3 headers in them. Make a program that searches those, that's able to search those things. So learning how to solve these kinds of computational problems, which has as its final stage, it uses your programming abilities. But even before that, before you start programming, you really need to think about what are the steps to solve this problem and how to do that. Once you've got a good idea of a sketch of a solution, then you can start programming it. And in this case, the programming is done in Python. So just becoming proficient in some programming language isn't quite enough. There's something else that I wanted you to not just solving small problems, but I wanted you to learn how to do a large, large in quotes here, because large really depends on on who you talk to, but for, let's say, a first-year programming course, a fairly large project, and I wanted also to have you use some third-party library. So you can't, not just something that goes and uses all of the basic stuff that happens to be in Python, but that you need some external support for. And this should have been from scratch. So not extending some existing application, but designing one and implementing it yourself from nothing. One thing that's forced upon us is learning about event-driven programming. So the standard, introduction to programming courses teach you about how to solve computational problems and how to implement them in some programming language, usually using the basic constructs of looping and variables and arithmetic. Event-driven programming is sort of a different model of programming where your program doesn't just run, but it mostly sits there waiting for events to happen that it then responds to in the appropriate way. And it's part of, for example, any kind of GUI programming, any kind of game programming, any kind of web programming is all event-driven programming these days. Another big one is I wanted you to learn how to use recursion. So how to define solutions recursively, how to understand recursive algorithms, recursive definitions, so how to use it and knowing its limitations. So I also wanted you to learn how to analyze the efficiency of algorithms, or if you like, programs. More or less the same thing. And then finally, last on the list is to learn how to do, let's say, rudimentary Java programming. Okay. So somehow these two things I view as a little bit less fundamental knowledge, these two with stars here. They're sort of things that we need to do to get you ready for what's coming later. Event-driven programming sort of falls out of using Pygame. The rudimentary Java programming, there's other things I would rather have done with the last 2 weeks of classes, but if I did, you would get to your next programming course and be completely lost. So I know from talking to students who took this course last year in Python that they really appreciated the last 2 weeks of learning Java when they got to 1406, the next programming course in our sequence. Okay. So these are the things I wanted you to learn. So do you think that we've hit these things? So whether or not you personally learned them, do you think we covered all of these topics? So is there anything that you feel maybe wasn't done? Okay, good. So let's turn these learning objectives then into basically a course outline of the stuff that we have learned and how it fits into to each objective. So becoming proficient in some programming language, and in this case Python, means we have to learn all kinds of things. So right on day one, we had to learn about variables, and we had to learn about types. So for example, numbers, which could be integers or floating point, and we learned about strings as well. So this is already in the first few lectures we learned about these things. And in fact, even in the first lecture, we learned about functions. So Python, it's just really easy to make functions, and so you make functions for everything. Next up was learning about something that's fundamental to just about every language that does anything useful, and that's arrays and lists. So how to define those, how to use them, what the purpose of them is. Next, we look at looping, and essentially, as soon as you start studying arrays, you can't avoid loops. So if you want to do something to an array, you have to iterate over its elements somehow. And so there we saw for loops, and we also saw while loops. And, well, related to that is branching. So for us, that was if, elif, and else statements. And then finally, we did user input. And this was basically enough to do basic text-based applications. So after learning all of these things, you actually knew enough to do text-based applications. In fact, your third assignment was to make a text-based game. So those are the basics. And 20 years ago, essentially that would have been what you learned in a introductory programming course. You would have been using a language that was so difficult to use that you couldn't get really beyond that. And it would have just been doing the details of that language. We pushed it a little further and did a few more advanced things. So stuff that would not have been in the curriculum 20 years ago. So I say advanced, but it just means, let's say, modern. One of the things we learned was exception handling. So as soon as you start taking user input, you need to deal with the case that users can do the wrong thing, enter the wrong information. And so in Python, that's with try and except. So we learned that very early on. Again, in a course 20 years ago, you would write a whole bunch of these applications that if the user did something like put in a digit where they shouldn't have, or put in a letter where they were supposed to enter a digit, the whole application would just crash. Not great. We also learned about objects. And objects come with a lot of baggage. So for instance, when you learn about objects, you learn about inheritance. Before that, you learn about properties, and what are they called? Methods. In other programming languages, these things are called instance variables, and instance methods, or instance functions. So, objects are these things that pull together a bunch of stuff, including some variables that we'll call properties, and some functions that we'll call methods that work on these objects. And they're organized in this class hierarchy, which has inheritance, and not necessarily related to objects. It doesn't have to be related to objects. There's this idea of polymorphism, that functions don't necessarily have to know exactly what kind of object they're working on. As long as the object supports the right functions, then you can pass it into to it. So as long as it has the right properties or the right methods, you can use it. So for example, many of the operators in Python are polymorphic. The plus operator accepts numbers, it accepts strings. In terms of numbers, it accepts different kinds of numbers, all of these things. Okay. We learned about object-oriented modeling. And maybe under this advanced category, we'll also say we learned about recursion. That came a bit later. Okay, so am I missing anything from that list? Can you think of anything else, really, that we learned about in? Yeah, so we learned about, let's say, more advanced data structures. So more advanced meaning more advanced than lists, and those were sets and dictionaries. So we learned how to use those things and what they're good for. Anything else missing from this list of topics? No. Good. And if you think about it a little bit, you'll realize that this was basically pre-midterm stuff. So by the time we hit the midterm, we had learned about all of these things, and more. And now, in terms of Python itself as a language, I don't think we really did too much more of any particular Python features. These are the main ones, and so that was, once you know this, and you know all of this stuff well, then you are a fairly proficient Python programmer. There's not too much more to learn about Python. Okay, so then the next learning objective was to learn how to solve computational problems. And we started out here already with assignment 1, doing what are called straight line programs. So in assignment 1, we had only learned about variables, types, and functions. We didn't even know about arrays yet. We didn't know about while loops. We didn't know about for loops. We didn't know about if statements. And when you don't know about those things, there's really only one kind of program that you can write. It's called if you also don't know about recursion, then you can only write these things called straight line programs. And straight line programs essentially are evaluating some formula. It's just one statement at a time, one line at a time. Maybe you assign the result of that line to a variable, so they can build on previous lines, but ultimately all you're doing is evaluating some formula. Maybe it's spread across multiple lines, maybe it's in a single line, and we saw lots of examples of these things. Compute the BMI, Fahrenheit to Celsius, all of these sorts of things are just simple formulas. Let's say formatting bibliography entries, those also qualify, right? You don't think of this as a formula, but this was a function which took some arguments that were strings, and then it combined them and returned another string. So it really, and the combination was really a formula. It was basically adding them together in some way with some other stuff. So very quickly, you reach the limitations of what problems you can solve with straight line programs, and then you start looking at more sophisticated things that can be solved with a single loop. So, for example, summing the values in an array. Computing n factorial. Give me another example of something you can solve with a simple loop. check if an element is in an array. So all of these things, basically, it's an iteration over an array, or iteration using a counter, and doing something at each step. And some of these things, sort of equivalently, you can solve them with a list comprehension. So, for example, squaring all the values in an array. So that's you could do it using a for loop, but you can also do it using a list comprehension, and it's a little bit more compact. Okay. We also looked at a technique. Well, I'll get to that later maybe. We also looked at problems that can be solved using a set or a dictionary. So what are examples of those kinds of problems?
If you can create another list of x if negative x is in the list.
Yeah, so finding elements whose negation, let's say elements of a list whose negation is also in the list. And we saw variance on this. I mean, that's basically the same problem as finding anonyms, right? So if you have a list of strings and you define, which is a dictionary, so it's supposed to be a list of words, let's say, and you define negation as reversing the word, then basically it's the same problem as finding the elements whose negation is in there. Finding all the unique elements in a list. So let's say some version of removing duplicates in a list. All of these sorts of problems where you need to look something up quickly, you can solve those in a set. And for dictionaries, I guess the main thing, the sort of main problem we looked at was frequency analysis, so counting the frequencies of occurrences of words. So there we had a dictionary whose keys were words and whose values were how many times each word appeared in some book or some body of text. Any other problems that you can solve using a set or a dictionary? So already you can sort of see that there's a similar flavor to the problems you can solve with a set, and maybe a similar flavor to the ones you can solve with a dictionary. And so as you get more and more experienced as a programmer, you will see problems and say, oh yeah, that's one of this flavor of problems. This involves removing duplicates, or this involves knowing for each element if some function of that element is also in the list, and so you'll be able to solve these things really, really quickly. Next up were problems that we could solve using sorting, and well, basically, most of the problems in the category above also fall into this category, but sorting is a little bit slower, so if we can, we prefer to use a set or a dictionary. But one of the things you can do using sorting is getting out, well, I mean, one of the things you can do is outputting things in sorted order. So that's almost the definition of sorting. But another class of problems are these order statistics problems. So, finding the median, or the 25th percentile, or the 75th percentile. Any of these things where you have a rank that you're interested in, and you want to know what the number is associated with that rank. So you sort everything, and then to find the median, you look at the middle element in sorted order, or you look at the element that's 3/4 of the way through in sorted order for the 75th percentile, or 1/4 of the way through for the 25th percentile. So these things are called order statistics, and certainly if you sort things, you can compute these easily. And we saw another class of problems that you could solve, which was solving problems using binary search. So for that, looking up a value or testing if a value is in a sorted array. Finding the first one in a sorted array of zeros and ones, and then this other weird problem that doesn't have a good name, so I won't bother writing it down. And the key there is that you should remember about this is binary search only works for very special inputs. Okay. So in particular, the input has to be typically sorted in some way that makes sense for the problem that you're looking at. So, searching for a value in a sorted array or finding the first one in a sorted array of zeros and ones, those kinds of things are, the input is very special. And it shouldn't be too surprising because binary search doesn't even look at all the elements in the array. So the array should be organized in some special way, otherwise, the solution you're looking for could be hiding anywhere, and there'd be no faster way to get it. Okay, so one thing to point out is sorting and binary search are related, right? So binary search works on sorted arrays. Sorting takes an unsorted array and sorts it. So a common mistake that a lot of people make is to think that, well, I'll just combine these two things all the time and then I'll always have, an efficient solution. So for example, if someone asks me to look up a value in an array, that's this problem here, checking if an element is in an array. Well, what I'll do is I'll sort the array and then I'll do binary search to check if it's there. So that's not a good strategy because sorting the array takes longer than just looking through the whole array. So the only time it would make sense to sort the array first is if you're going to ask a lot of these kinds of questions of, is this value there, is that value there, is some other value there? So it's only worth sorting it if you're going to ask these questions repeatedly. It's not worth sorting it to get the answer for one question. But that's sometimes hard for people to remember because they remember that sorting can be done efficiently and binary search is very efficient, so they think combining the two must be really efficient too, but it's not. If you can solve the problem just by scanning the array, that's faster than sorting it and then doing binary search. And then finally, we looked at, solving problems using brute force. So here, for example, I give you a problem that's like, Bentley's problem, for instance, which says, find the indices I and j which maximize the sum AI plus 1, AI plus 2 up to aj. So unless you are really able to analyze the structure of the problem carefully, basically the standard solution you come up with is enumerating and testing each pair of indices, I and j, for an array. So for example, any question which asks you to find a pair of things in an array, you can solve it by just enumerating all of the pairs and then checking for each pair if it satisfies what the question is asking for. Same thing with triples, same thing with whatever you want. In fact, we even saw the ultimate of this thing is computing the power set of an array. It gives you every subset of elements in that array. Unfortunately, the power set is huge. If the array has length n, the power set has size 2 to the n. So for example, if there's 32 elements in the array, your power set has size 4 billion. And so it's not a terribly effective or efficient way of doing it, but it may be the only thing that's available to you. Okay. So those are basic tricks for solving computational problems, and this is not an exhaustive list of tricks. You know, researchers are coming up with new solutions, new techniques every day for solving different kinds of problems. But this is let's say, the most common ones, the ones that you're most likely to use in the real world, let's say. Okay. So the next learning objective was for us to learn how to do a large project from scratch. So how did we meet that objective? What's that? Well, using objects, yes, but I mean, to learn how to do a large project from scratch, you have to do a large project from scratch. So what was that large project? The game. So assignment 8. This was a game with a fairly long feature list. You had to do it from scratch, basically. Maybe you could pull in some code snippets from different places, but you had to do it from nothing. And it does use a third-party library. It uses Pygame. So, and during this course of doing this assignment, many of you explored the Pygame library, found things which I hadn't talked about in class, and that's good. That's basically what happens when you do real programming in an industry environment. Is you're usually working with these huge libraries, and nobody's going to teach you everything about those libraries. You just you learn about them by exploring them, and occasionally you submit some code, you go through the code review process, someone says, hey, you wrote some code that does this. The library already has a function that does that for you, so you erase that code and use the function instead. But that's how you learn about these things, by exploring them. So I think we did that. To learn about event-driven programming, well, we killed 2 birds with 1 stone. Pygame and almost every other graphical user interface programming environment is event-driven. So your game sits there in a loop, the main loop, and it sits there waiting for events to happen. When an event happens, it looks at the event type and goes and takes the appropriate action based on the event type and any data that's associated with that. And then that sort of becomes a weird way of thinking about things, and requires a way of structuring your program so that the data you need is available to you. And this is somehow where objects came in handy here. So by putting your event handling loop inside an object, well, all of the methods that handle these events, they have all of the object's variables available to them. They have all of the object's functions available to them. In particular, the whole state of the game is there in that object and available. So it's a handy way to do things. And I know, for example, in assignment 3, which was also programming a game, a few of you had this difficulty of not being sure what to do, because your game was essentially a bunch of functions, and every one of those functions needed to know about the whole state of the game, and so you ended up having to pass these arguments into functions and stuff. It was kind of an awkward way to do it. So you ended up having to pass a bunch of arguments into a function or an array into a function, sort of a hacky way of doing it. Objects solve that problem nicely. They preserve all the state and keep it available for any method within that object. Okay. So learning how to use recursion. This sounds easy, right? You just make a function that calls itself. But there's actually a lot of pitfalls that you can make here. So what are the dangers of using recursion? So infinite recursion, which then manifests itself as a infinite loop. So you have to avoid infinite recursion. And what's another pitfall of using recursion? What's that? Well, I mean, there's some overhead or slowdown, but that was never really much of an issue for us. So I wouldn't worry too much about that. But what's the bigger danger? Yeah. So Stack Overflow. So this occurs when the recursion depth is too high. And in particular, at least in the version of Python that I've been using, about 998 stack frames is too much. Or maybe 998 is okay, but 999 is too much. So to understand these problems, you need to understand how recursion works. So you need to understand the runtime stack, which is basically this list of stack frames where you have one stack frame. Every time you call a function, a new stack frame for that function appears on the top of the stack. When the function returns, it gets popped off the stack. So every function call creates a stack frame, and stack frame gets popped off when the function returns. So you really needed to know about this thing. And as a side effect, as a bonus, you learn about variable scope. So you learn why it is when you define a variable inside a function, you can use that variable inside that function, but then you can't use it later outside. And that's just because when you call the function, a stack frame appears. Inside that stack frame is that variable. When the function returns, the stack frame disappears, so the variable is gone. So you learn about this thing called scoping. And scoping is a rich topic. If you take a course in compilers, or you take a course, when you take a course in programming languages, you'll learn that different languages have different ways of handling scope. But you've learned about variable scope, and in particular, local scope. So variables which are local to a function, you can access them in the function, but once the function returns, that's it. They're gone. So we got that for free when we studied stack frames. And we basically learned a recursion recipe, which was you have to be able to handle small problems without recursion. That's the first part of the recipe. So for example, factorial of 1 equals 1, and factorial of 0 equals 1. Those are the small problems. And once you've handled the small problems, well, then you need to be able to deal with the big problems, and that's where you use recursion. So be able to turn a big problem into a smaller problem. So notice that it's not necessarily a small problem, it's just smaller than it was originally. And for things like factorial, factorial of n is just equal to n times factorial of n minus 1. So the problem, if you think of the size of the factorial problem as being n, I took this problem which was of size n, and I made it a little bit smaller. Which means that eventually, if I keep doing this, it will become small enough that it's one of these things that I can handle without recursion. So these small instances are called the base cases, and the big ones are, they're not called anything. They're just the main cases, the recursive step. And that's for most problems that you solve using recursion, except for some really strange ones. That's the recipe. So be able to express the solution of a big problem as a solution in terms of smaller problems, and then be able to solve tiny problems easily. So another example is merge sort, or merge sort of A is just A when the length of A is less than or equal to 1. So that's the small problems that you can solve directly without recursion. And if you have a big problem, then merge sort of A is just the merge sort of A up to the middle element, and the merge sort of A from the middle element to the end. So it doesn't just have to be that you reduce your problem to one smaller problem. You can take one problem and turn it into two. That's what merge sort does. And as long as both of those problems are smaller than the original one, this will eventually finish. So in this case, if A has length n initially, this has length n over 2, and so does this one. And as long as n is bigger than, this one has length n minus n over 2. As long as n is bigger than 1, both of those things are smaller than the original problem. Okay. And one of the things that we looked at sort of briefly that you should at least know it, recognize it when you see it, is the problem of avoiding high recursion depth. So things to avoid turning a problem of size n into a problem of size n minus 1. If you turn a problem of, the way of solving a problem of size n is to solve a problem of size n minus 1 recursively, you'll get a recursion depth of n, because this will go on, a big stack of these things right up until the case where you reach the base case, n equals 1 or 0, and so you get a recursion depth of n. Better to turn a problem of size n into problems of size n over 2. So if you can do that, then you get so if you do the top one, you get a recursion depth of n, and if you do the bottom one, you'll get a recursion depth of log n. And if you remember, n and log n are very, very different. So when n is 4 billion, log n is 32. When log n is 1,000, for example, which is the maximum recursion depth you can have in Python, n is a number that has about 333 digits in it. So, so lots of, I mean, a number with 330 digits, that's not going to be the size of the input to any problem that you're given. It's more than, for example, the number of atoms in the universe. So there's no memory big enough to hold a problem that big. Okay. Next up on our list of learning objectives was how to analyze the efficiency of algorithms and programs. And so we had developed a tool for that, which was this big O notation. So this basically hides the constants in a formula. Focuses on the big picture. And we saw a sort of hierarchy of the common running times you run into, which are, for example, O of log n, that's really fast, much faster than O of n, which is faster still than n log n, which is faster still than n squared, which is faster still than n cubed, and so on. And we've actually seen examples of all of these running times. Here we see binary search. Here we see simple sort and scan. Here we see things like merge sort. Here we see the solutions which test all pairs of indices. And here we see solutions which do things like test all triples of indices. So actually, if you look at our list of problem-solving techniques for solving computational problems, they basically generate algorithms with these kinds of running times. So, you know, a running time of O of log n comes from some variant of binary search. So that means it eliminates half the input in constant time. In the case of binary search, it eliminates half the input by doing one comparison. O of n, these are the usual single for loop that scans an array or counts to n or counts down from n, whatever. Also in here, you'll find list comprehensions. So a list comprehension which takes one list and turns it into derives another list of the same length from it. That's because a list comprehension really internally is just one of these for loops. O of n log n running times. This is the time it takes to sort. So we've, if you call a Python sort function or you use merge sort, that's the running time that it takes to sort this array. And O of n squared, that's, for example, the time it takes to enumerate all pairs of indices in an array of length n. And I should remind you that this variable n here refers to the size of the problem. And usually the size is pretty well understood. Usually the input is in a list or an array, so n is just the length of that list or that array. And O of n cubed, there's a couple of ways to get this. So you could, for example, enumerate all triples of indices. So find all the integers I, j, and k where I, j, and k are between 0 and n minus 1. That would take n cubed time. But another way to do it, for example, is the obvious solution to Bentley's problem. So Bentley's problem is this one that says, I give you a list that has positive and negative numbers in it. Find the sublist which has the largest sum. And so the obvious solution is to say, well, I'll enumerate every I and every j, and then I'll compute the sum between from AI up to AJ, and I'll keep the maximum sum that I encounter. So why does that take n cubed time? Well, it takes n cubed time because there's n squared pairs of indices I and j, but you don't just look at the two elements I and j, you actually add up all the numbers in between them. So that gives you an extra factor of n there. So, and then the other thing is, I don't want you to think that this big O is something that's just, you know, pie in the sky, some kind of theoretical tool that nobody ever uses. When you're thinking about big O and whether this is a good runtime or not, put in some real numbers. So, you know, put in real numbers there. For example, look at what these things give you when n is 10,000. Then you get things like, you know, log n is about 14. Well, when n is 10,000, n is 10,000. And log n, well, that's about 140,000. N squared, well, that's 100 million. And n cubed, well, that's a number with, it'll have 12 zeros after it. So that's that number there, which is, here's a billion, it's 1,000 billion, so I guess that's a trillion. So that's like, this is about, if you measure the debt of the United States, it's measured in these units here in dollars. Big, big number. So that means, for example, it takes a while for a computer to even count that many dollars if it's counting them one at a time. Okay, so, you know, n is 10,000 is a nice, good number to use because it actually shows you when things start to become impractical. And it's not a huge number, right? Think about all of the things that, that you could have where n is 10,000. Just my own fairly small CD collection already had 5,000 songs in it. You know, take a collection that's twice the size of mine, that's 10,000 songs. You don't want to run an n squared algorithm on that. It's going to, you know, if you have a music library and it uses somewhere an n squared algorithm, well, that's going to do something like 100 million operations to do whatever it's doing. So there you go. And we also took a look at, because we wanted to have some real concrete things to analyze, well, we looked at the efficiency of binary search. That was O of log n. We looked at the efficiency of some sorting algorithms. And we only did two this time. Bubble sort, what was the running time of that? Was n squared. Bubble sort is basically two for loops, two nested for loops. Each one runs n times. The outer loop is just there so that the inner loop runs n times, and the inner loop just does this comparing adjacent elements and swapping them if they're out of order. So that was n squared. And merge sort, this is this thing that we analyzed very carefully looking at its recursion tree, and we saw that its running time is order n log n. So we did that. And the hardest thing we probably did in this course was analyzing the efficiency of recursive algorithms. So here we looked at the recursion tree. So we draw this tree that shows the stack frames at different points in time as the algorithm executes. And related to that, we also looked at this, what are they called? Recurrence, we call them relations for the running time. And just as the example of that, so for some people it's easier to understand and draw recursion trees. For other people who are good at symbolic manipulations or good at algebra basically, it's easier to do these things with recurrence relations. So for example, binary search is the easiest one. And basically, binary search, if you want to say what's the running time on an array of length n, well, you do one comparison that takes constant time, and then you're left with an array of length n over 2. So the time it takes to solve a problem of size n is the cost of that one comparison plus the time it takes to solve a problem of size n over 2. And then you can play with these recurrence relations. And notice, for example, that usually what you do is you just keep applying the definition until a pattern pops out. So how long does it take to solve a problem of size n over 2? Well, it takes time to do that comparison, and then I have to solve a problem of size n over 4. And how long does it take to solve a problem of size n over 4? Well, I have to do that comparison, and then I have to solve a problem of size n over 8. And if you keep doing this, eventually you get down to a problem of size 1. And that we know how to solve. That just gets solved directly. And how long does it take to get down to a problem of size 1? So how many times can I divide n by 2 until it becomes less than or equal to 1? Yep. So remember that. Important. Log n is the number of times I can divide n by 2 before the result is less than or equal to 1. Okay. That'll be our working definition of log n. If you don't understand exponential functions and you don't remember any of that stuff, that's fine. Just remember log n as being defined as the number of times I can divide n by 2 before it's less than or equal to 1. And another one to remember is the running time of merge sort. So we showed that that's O of n log n, and we actually did it two different ways. One was by looking at the recursion tree, and the other one was by looking at this, these recurrence relations. Both of them work. Okay. And then our last learning objective was learning how to do rudimentary Java programming, so the basics of Java. And there, because you had already learned a programming language, what we had to do, or all we had to do, was focus on the differences. And those were the main difference. Everything in Java has to have its type declared. So you have to specify the type of everything. So that means typed variables, typed function return values, and typed function arguments. So Java's types, there were things like short, int, so there's integer types that look like this, short and int. There were floating point, those are called float and double. And then there's strings, objects, and so on. There's also characters in there. And Boolean. And one thing to look out for is Java's integers can overflow. So for example, the limits on the int type are roughly -2 billion up to +2 billion. That seems like a huge limit that you would never run up against, but for example, if you multiply 1,000,000 times 1,000,000, you fall outside that range. It's actually quite easy to blow up one of these types. Okay. There are these access modifiers. Public, protected, private, and there's even one called friendly. So in Python, everything is public, meaning that it can be accessed by anything at any time, anywhere. In Java, there's all these modifiers that say things like, maybe it can only be accessed in the subclass. Maybe it can't be accessed by anything other than this class. Maybe it can be accessed by the subclasses and as well as things in the same package. Don't worry about exactly all of what those things are, but just know that public corresponds to the situation in Python where you can look at anything. For example, in Python, we defined objects that had variables, let's call them x and y. Then in some other function that has nothing to do with that object, you could look at x and y. No problem there. We did that all the time. In Java, you wouldn't be able to do that by default unless those things were declared to be public. Static versus non-static methods/functions. And in Python, we have functions and functions within an object. So in Java, everything is inside of an object or inside of a class. And so if you want just a plain old function that anybody can use, you have to declare it as static. So that's why Java has this notion of static. Static gives us a plain old function that we don't need an object to use. In Python, these are just the functions that you define at the top level. Java has arrays, and it also has the basic data structures that we find in Python, which are list, array list. Those correspond to Python's lists. We have set and hash set for Python's sets, and we have map and hash map for Python's dictionaries. Now, this is probably, in terms of Java lessons, this is probably the most important thing you'll take out of this intro to Java thing. This will put you ahead of many, many novice Java programmers. Because you know from using Python how to use sets and dictionaries and lists and how powerful they can be. Because they're a little bit more complicated to use in Java, while many programmers just don't learn how to use them, or they avoid them, or they only learn how to use one, which is lists, and so they end up with these really inefficient things. Don't be afraid to use all three of these things if they're appropriate for the problem you're working on. That will make you a better Java programmer than 80% of Java programmers out there. And then another fundamental difference was exception handling. So very similar, but you say try catch instead of try except in Python. But otherwise they look the same. Okay, so I think that's a pretty exhaustive list of the topics that we've covered. So now we'll get to the part that you've all been waiting for, which is what's going to be on the exam. So the exam format looks like this. 50 multiple choice questions. 25 of those are pre-midterm material. 24 of those are post-midterm material, and one of those is a bonus question, which you can't study for. Unless you're, the way to study for the bonus question is to learn, read all of Wikipedia, and then you may be able to do that. Plus all of the, every, serious book ever written, then you may be prepared for the bonus question. So I wouldn't recommend bothering to study for that. It's 2 hours long. And here's the breakdown of topics. And we'll go backwards here. Nine questions will be Java, mostly comparing it to Python. So those would be questions like, here's some Java code, here's some Python code, do they do the same thing? If I did something this way in Python, how would I do it in Java? And the multiple choice version of that thing. 9 questions, analysis of algorithms and recursion. So these will be things like what is the running time of this function when n equals 10,000? So I'll give you a function and say, what's the running time when n equals 10,000? Or more specifically, how many times does this line of code execute? What is the recursion depth of this function? That's another one. Usually with some fixed value of n. Remember the definition of log n. This is important. Some examples. What's log of 8? 3. Divide by 2, you get 4. Divide by 2, you get 2. Divide by 2 again, you get 1. So you have to divide 3 times. What's the log of 256? 8. And what's the log of 10,000? Roughly. It's about 14. Practice drawing recursion trees for some functions. So on the midterm exam, you guys, many of you left very, very early. The majority of the class left after something like 25, 30 minutes, even though the exam had an hour and 20 minutes available for it. So that means that you were reading questions and picking the answers and checking them off without thinking too hard about it, because there were 25 questions. So that means you're spending about a minute or so on each question. Here, some of these questions will take some time. So don't be afraid to, on the margins of the paper, start drawing a recursion tree. Do a little example. If I ask you a question about something where, how long does this take, or what's the recursion depth when n equals 8, then you can draw the entire recursion tree and know the answer to that. It takes a little while, but you have 2 hours. So reading the question and checking the boxes is not going to take much time. Use your time to think about these questions. Last year, similar thing happened in the final exam. People left after 30 minutes, 40 minutes, and I thought, oh geez, I made this too easy. And then the marks came, and I realized I hadn't made it too easy at all. People just weren't used to spending some time thinking about how to answer a multiple choice question. If the answer is not right there in the top of your head, well, sit down and think about it. Next up, 10 questions on sets, dictionaries, arrays, and/or binary search. So these will be things like, knowing whether you should use a set or a dictionary, or whether it should be binary search, or whether binary search is applicable, or which is preferable. Should I use a set, or should I use binary search and a sorted array? So things like choosing one option over the other. And it's never a good idea to first sort and then use binary search. Unless you're planning on doing a lot of searches. Because, like I said, scanning the array is faster. Yep. So why is it not a good idea? Yeah, because if you're doing that because you're looking for one particular value, just scan the array and find that value. Sorting it takes longer than that. Yeah.
Do we need to worry about a pre-solve and in the binary search we have a pre-solve, we have shell, we have bubble solve?
Well, you need to worry about the sorting algorithms that we've analyzed, for example, in class. So. What more do I want to say about that? There will be 4 questions about object-oriented programming in Python. So those will be things like a class hierarchy, and the inheritance that comes with that, And remember, yep.
Referring to the is has thing?
Well, the class hierarchy stuff is, you know, knowing if you have two classes, one is a subclass of the other, and I make an object out of the subclass and I call a function, which of the functions executes, those kinds of things. And here, remember what happens when you override equals. That actually changes what it means for two objects to be equal, and there's this stuff about overriding. If you override equals and you use sets, you also have to override hash. And then finally, 3 questions about arrays and aliasing. So what's aliasing? That's this question of is versus equals. So it's called aliasing because when you have two variables that refer to the same array, well, you say that this one is an alias for that array, for the other one, or they're both aliases for that array. There are other names for the same array in memory. And then 12 questions on Python programming basics. And those are things like, what does this code do or return? Okay. All right. So that's the overview of the exam format. And so maybe next class, all I will do is bring a bunch of maybe sample questions that, you know, from these different categories that we could do together. Or if you have your own questions, go ahead and bring them with you. So that's it for today.